So let me give a very introductory talk about how to construct and study P-Adic cohomologies using motivic homotopy theory. And actually, I will start with an introduction about one of the first reasons why rigid geometry was introduced. And the motivation for doing so was to construct a bridge, say, from characteristic P onto characteristic 0 in the following situation, in the following sense. So maybe you start, so create a bridge from car P in the following idea. So let's fix, for simplicity, a finite field. Let me even fix Fp, and suppose I have an X which is moot over Fp. Now, it would be nice if we could, say, develop some well-behaved de Rham cohomology theory, even for arbitrary smooth varieties like these. And but we know that in characteristic P, this is not really possible. So this could be a motivation to start trying to move this variety into characteristic 0. And the naive picture would be, hey, what if I place my basis Fp inside a frame and I consider it as simply a fiber into a maybe Z, which is a curve, and maybe I can extend my family X that was living over this point into a nice enough family over the whole space, over the whole frame. And now that I converted my X into an actual family over Z, I'm able to, say, take the generic point over Q. And therefore landing finally in characteristic 0. Now, as you can see, this functor does not really exist. There is no way I can spread out canonically something from this point over the whole curve. So more realistically, what people did was like, OK, since I start over this fiber at Fp, maybe what I'm allowed to do is not really going all over the place, but staying around infinitesimal neighborhoods of this talk inside this frame. And when you talk about such infinitesimal neighborhoods, I mean talking about formal schemes. So let's say iadically complete rings. Therefore, you still might believe now more optimistically that there is a functor from varieties, say, over Fp going to, say, formal schemes, smooth, maybe smooth, everything is smooth. Over Zp, which is now the completion of this frame at this point. And then once you're here, once you have now spread it out into a formal scheme, the only way you can make sense of a generic fiber functor is to consider rigid analytic varieties. So because once you are in this situation, you cannot hope to have an actual scheme over Qp. But what you can do is take the generic fiber and land into, say, smooth rigid varieties over Qp. But now, even though this seems more plausible than before, this cannot be done in the sense that this functor doesn't really exist. And we want to reply to the following questions. Maybe I cannot really stay at the level of geometry just thinking about varieties. I have to massage them and allow some extra flexibility so to be able to define this functor. So can this squiggly arrow be rectified? This is a one way. This is a modern way. I mean, maybe if I have time, I can say if there are bridges between these two constructions anyway. So let's stay classical from the moment. And so, but I will eventually talk about bit vectors and stuff. Can we rectify this? And maybe can we even go, so this would allow us to go from one side to the other side. Now, at this level, of course, I also have classical smooth varieties over QP that via analytification can be translated into analytic varieties. So maybe another question would be, can I go back and associate it to a generically smooth family, something over the missing fiber? And this will be a question I will try to reply on the second half. And can we revert it? And what do we lose? How lossy are these functors? Now, of course, as I was mentioning, one cannot hope to consider just schemes. We need to introduce some X-like degree of flexibility, which is suggested by the following classical results in the formation theory, which are due to Grothendieck and Elkik. So more generally, rather than just sticking to FP, I can fix maybe S, which must be thought as maybe a ring A modulo some ideal I. Now this ZP will be replaced by the formal scheme obtained by completing A with respect to I, and here I would take the generic fiber of this formal scheme. So anyway, they say that first of all, the category of Ertl varieties over AI is indeed the same as the one over this completed ring. So there is a way to canonically lift Ertl maps. This also tells us that if I'm smooth, therefore I'm locally Ertl over a ball. Balls can be easily, affine spaces can be easily lifted. So indeed, if yes, okay, let me be more precise. If R bar is over A mod I smooth, then there exists a smooth lift, affine. Yes, so this is an affine scheme. So this is there exists a smooth lift to A hat. They are all possible lifts are all isomorphic to each other, and even maps between smooth things over A mod I can be lifted. Yes. Now, this may suggest to you that it will suffice to work locally to transform these equivalents into something holding for smooth varieties, but this does not imply this. It's not true that that there is an equivalence between smooth varieties over AI and smooth formal schemes over A hat. This tells you that locally any smooth variety can be lifted, but the problem is that even though these lifts are all isomorphic to each other, they're not canonically isomorphic to each other. And even though I can lift maps, there is no canonical lift of such maps, so you cannot hope to have such a thing. But these results have been refined by Arabia, telling you that any two lifts of the same map are actually homotopic, meaning that there is a homotopy like this that would be a homotopy between the two potential lifts of the same map you were describing below at the level of A mod I. Okay, so these results suggest us what to do, how to replace and or maybe like massage, introduce further flexibility at this level. We should make sure to identify homotopic maps. And one naive way to do that would be to identify these two objects, namely to contract the affine line. If I did that, then the two maps would really become equivalent. and therefore having a unique lift. Is the completion of the polynomial ring. It's just A1. Sorry, these are now formal schemes. I'm sorry. I apologize. Yeah, R bar are here. So now R's and S's are my lifts, and I apologize. So I would have something like this. Thank you. OK, great. Oh, so how can we formally invert homotopies? Well, we are now very well used to doing such things by localizing an infinity category. So the classical definition following Vygotsky and others would be to do that. So let's say that dA effective over a certain base S will be, by definition, I take the derived category of Ertl sheaves of smooth varieties over my S with coefficients in Q, and then I invert formally homotopies, meaning that I can take the full subcategory of the category of sheaves such that those do not see the difference between A1 over X and any object X. And this is the description as a subcategory, but there is, as we know, there is even a left joint functor that allows you to somehow translate any given sheaf into a ball A1 invariant one. OK, so this is the definition of motives. But you can see you can do the same construction out of an arbitrary situation. In particular, even if S was now a formal motive, I could do the same trick by replacing this site with this other site, if S was a rigid analytic space, or you name it. Now, in all my talk, I will be very basic, and I will always consider Ertl sheaves with Q coefficients. Most of you will be very much, how do you say, sad about the fact that I'm inverting P, but that's life. As soon as you want to do A1 invariant cohomology theories, you have to pay a price. And the toll is now that, say, you have to say goodbye to crystalline or prismatic or whatever. OK, so that's my tariff. Now, this is enough for the purposes of the motivations that I sketched before, but let me even introduce another variant, which is, again, obtained by universal property. Out of the category I defined above, what if I also invert the Tate twist? Meaning that I make sure that the first cohomology of GM is a line bundle, is invertible. So Q1 will be the direct one piece of the motive attached to GM. Over here, GM decomposes into two direct factors. One is the constant one, the unit, and then there is another piece, which is Q1 shifted, and you decide, you simply impose this to be invertible. OK, so these are my motives, and as I told you, again, you can consider them in various situations. OK, so how? Yes, that's called, yeah, maybe not for dA, but for dM. Yes, cancellation theorem.
Yes, and this holds in this
No, not in general. Not over an arbitrary base, not even for Vygotsky. OK. That's not going to be relevant for what I'm saying, but anyway. OK, so what is the translation of this fact? It can be translated into the following theorem, which is by Joseph Ayoub, which tells you that if S is a formal scheme, then motives over it, how do they compare with motives over their special fiber? Well, they are the same. And this is the functor, which is obtained by universal property, sending X onto its special fiber, which is smooth over the special fiber of S. Okay, so finally, I hope I convinced you that this theorem gives a positive answer to this squiggly thing, because now if I have a variety over S bar, say, or which is sigma, the special fiber of some formal scheme S, I can attach to it a motive. Now, with this equivalence, I can canonically lift it to a formal scheme over S, except that it's no longer a formal scheme, it would be just a motive. So I have straightened my squiggly arrow that I defined before. And now here, I can finally take my generic fiber and go, if I want, over motives over the generic fiber, which I will denote with the prefix rig, for standing for rigid analytic motives. Not here. I might tell you when it will become important. How about P? I'm taking rational coefficients. I mean, I'm taking Ertl motives, so inverting P somehow inside the. But yes, it's not important. It's like as soon as you invert, yeah, such things hold even without coefficients. Okay, so, and now the question is, are there, now that I have developed this new, so by the way, the proof of this theorem is not at all, does not follow, is not like it's a corollary of Arabia's result. It's proven in a completely different way. But anyway, it's, I think it's a nice, anyway, now that I've developed this new theory, the one of motives, and I've used to iron away some wrinkles that I had before, can I use the same product to solve other classical questions, other situations where I can use motives to straighten, strictify, or whatever classical constructions. So let me name two of them. One would be related to spreading out. So we all know that CP is the union of finite extensions of QP inside CP, and then you complete it, meaning that in using Huber's tilde limits, CP can be seen, the spectrum of CP is the limit of the spectra of these finite extensions of QP. And we also know that if I have something smooth over CP, a rigid analytic variety which is smooth over CP, locally it is given by a bunch of polynomials, and I'm totally able to descend and finding a model over a finite extension of QP for any such. Nonetheless, so I can descend locally smooth varieties, but I cannot find models of maps in generals. For instance, if I simply took the map, say, from the circle to CP that is hitting a genuinely transcendental element, something which is not in the union, but it's really arising from the completion, then there is no way that this map will have a model into a finite extension of QP. So, but we have the implicit function theorem. Because we are analytic, we know that as soon as I have one map between smooth varieties, I can maybe hitting, like, determined by a bunch of elements in the target, I can move a little bit around these elements and still find a new map, hitting now elements which can be arbitrarily close to the chosen one. In particular, this map can be massaged and modified into one that does land in some finite extension of QP. And so up to homotopy, I can descend maps. And once again, this fact admits a motivic counterpart, which is proven in a joint paper with Joseph, Martin, Gallauer, and myself, saying that if I now take motives over CP, well, they are literally the same thing as motives over finite extensions of QP by taking them all together. Now, and this more generally holds if I take S to be a Huber tilde limit of, say, affinoid spaces, the same result holds. So you can spread out along such delta limits. In particular, you can deperfect. I mean, if you take a perfection as the limit of a tower or whatever, and you have something smooth above, you can always force it to go down below canonically, except that now we are taking a motive. In PRL omega, in PRL, yeah. In presentable category. So compact objects are literally the union, and then you have to take the ind completion. Yeah, it's not a co-limit in infinity categories. Yes, because this map is indeed induced by take the special fiber. So if something is an inverse image of that, then it has to be its canonical lifter. Now another situation is when taking dagger spaces. Now the problem is that the RAM cohomology is still bad on rigid analytic varieties over QP, in the sense that it is not ball invariant. The ball has a huge H1 group. So how to change that? So the classical fix, following ideas of Berthelot, Monsky, Washnitzer, and Grosse-Klone, would be to equip any variety X over QP with a dagger structure. Meaning that you choose a place in which you embed it strictly. So say you take the ball, and you do not simply see it as it is, but you embed it inside P1. Yeah, so what Offer is suggesting is that, but this is not a functor. I cannot canonically equip any variety with a dagger structure. It's really a choice of an embedding. And then what I'm saying is that, but now, because this is not a functor, okay, but every time I have two maps, or one map here from X to Y, is there a way I can choose a dagger variety on the source and on the target such that this map extends to a map of dagger varieties? The answer is no, but at least up to homotopy it does. So again, up to homotopy. This is the so-called Artin's approximation lemma by Bosch. Every map can be extended to a map of dagger spaces, dagger varieties, locally. Everything is smooth in my mind. Yeah, smooth. Locally, so affinoid is fine. Okay, what is the translation of this fact? Well, I guess you can already tell. If I take rigid motives, maybe dagger ones over a dagger base, and I forget the dagger, this lands into the motives over the actual base, the one I'm starting with, and this is again an equivalence. So this is another way you can rephrase a classical statement into an equivalence of motives. Okay, but so far it seems like these motives are just a nice black box where I just stash in many classical statements, and I don't get really nothing new because more or less all these things were already used in the classical literature. And but now let me try to make the point that sometimes these constructions and these definitions can be actually useful to prove something new about P-Adic cohomologies. Yeah, indeed. So this theorem tells you that precisely. Now, at this level, I do have a nice de Rham cohomology, right? Because if I start with something dagger, they are well behaved. What is this? This de Rham, which lands in quasi-coherent modules over the base, in the sense of Clausen and Schulze. Well, let's say that the usual omega complex of X over the base gets replaced to one which is the one of those which are over-convergent with respect to the base. So let me stick to the absolute case for simplicity. So if X was now a smooth variety over K, I can choose a dagger structure over it, and instead of considering the whole complex of all differential forms, I simply take those which extend onto a strict inclusion. So this will be the union of all the differential forms that extend into a strict neighborhood of my X inside the chosen ambient space X prime. But as you see, it depends heavily on the structure of a dagger variety that I've chosen. So it is a priori only well-defined over there. But thanks to this equivalence, I can define also de Rham cohomology from here. Is that what you were saying? Yeah, I mean, more or less that's what they were doing. Like, oh, let's check it is well-defined. Oh, let's work locally. Oh, there is a homotopy. So, I mean, morally, it's... Sorry, I'm not trying to diminish... I mean, the ideas were the same. It's just a way to put things in a nice gift box with a ribbon on top. But yes, these are classical constructions by Monsky, Washnitzer, and Ertl and Grosse-Klone who did this. Grosse-Klone?
No, I don't know all the previous. I mean, I'm not completely. So, if you have a smooth rigid analytics, even I don't know.
Yes.
You want to associate it with finite-dimensional de Rham cohomology.
Yes.
By using this idea of Monsky-Washnitzer cohomology. So could they construct this cohomology theory?
I think so, yes. And the idea, Grosse-Klone. And the idea, maybe he would tell you that HI is well-defined because locally any choice of a dagger variety would not depend because there is a homotopy. So it boils down eventually to the same ideas. That's what I'm saying. This is just a way to put them all together. Okay. But these are not the applications I had in mind, or at least not only those. Now some actual extra results. Now, say I fixed now my S, which is a scheme over FP. And now, as in my introduction, I fix a frame over S. So in my introduction, I had to place S in a family or something. Let me be slightly more general than that. So I fix a formal scheme S, a map between the special fiber of this formal scheme to the scheme I am starting with. And then I take the QP rigid analytic variety attached to S, and I choose a dagger structure of it. Okay, so I have my S, I lift it. I have a map from this special fiber, which is inside this S, which has a P-Adic generic fiber. And of this guy, I then choose a dagger structure. OK, every time you have that, then if you start with motives over S, you can base change and go to motives over this thing. Then these get identified with formal motives over this formal scheme. Now they go to rigid motives over this generic fiber, which are the same, I recall, as those over this chosen dagger variety, dagger structure I put here. And now, as previously spoiled, there is the RAM realization, dagger the RAM realization, landing in this quasi-cos a la Clausen-Schulze. And so in the same way as this recovers Grosse-Clone over convergent the RAM cohomology, this is an instance of the classical relative rigid cohomology a la Berthelot, which is finally a way to define a relative de RAM cohomology for schemes that live in characteristic P. So you choose a lift and you do that. And now the theorem is, which is a joint work with Veronica. Where is moot? No, schemes over S are smooth. I mean, let's say motives are defined out of things which are smooth over S. But in 1 second, I will tell you that even singular things will have a realization. Is that what you're asking? Exactly. Let's say at this moment, yes. But then I will come back to your question. It's not a formal model a priori. It's just somebody mapping to it, because a priori it might, in particular, it might be the identity if you want. It's a generic fiber of this formal scheme. Yeah, this is, as I say, it's a P-Adic. It's a living over ZP. I just take the.
How do you take the RAM cohomology of this? You want to take the RAM relative to S.
Yes, exactly.
Now there is nothing relative to S. In the general fiber, you take it could be singular because it's singular. So
yeah, but it's X living above it. It's smooth. So there is this. In order to define this, I take an X dagger, which will be smooth over S dagger, and there even the map is smooth. So there is a way to have a well-defined RAM realization. It's the base, the dagger structure I've chosen on my generic fiber.
okay, you are doing this
Okay.
I lost a little bit.
I'm sorry. Yeah. S is not smooth, but everything you can, at each stage, you can stick to things over, which are smooth over it. So the theorem with Veronica is that if X over S is now proper and smooth, and let me call this the relative rigid cohomology, I don't know, R gamma the RAM or something, then R gamma the RAM of my X relative to the chosen frame I have fixed is a perfect complex. Which allows me to extract its ith cohomology groups, because this has a T structure. And they are not simply coherent modules over this dagger space, but they're even vector space, vector bundles. Yeah, locally, sorry. Locally so. If at each, locally, if you restrict this onto each affinoid opens. let's say I want to.
Each cohomology group has a quasi-coherent sheet is actually a vector bundle.
Yeah, sorry. I probably have said something wrong in between. I apologize. I am sorry. And so this means that by letting frames vary, I can take this category of frames over S, and for each one of them, I would have a different realization, and there would be compatibility between them, because every time I have a map of frames, there would be a compatibility between the realizations. So I get a canonical structure of a overconvergent F isocrystal. On these things. Meaning that it's literally an object in this inverse limit of vector spaces over these guys by letting this vary over frames. And then I also have a descent, a Frobenius descent datum. Okay, so, and this theorem was not known in this generality. This was previously known only for globally liftable varieties, or for, so by work of Berthelot and Suzuki, or in using alternative approaches to rigid cohomology, for example, the one by Kato of over holonomic D modules, alternative settings. Let me give a sketch of a proof now. And here I drop the bomb. I drop the fact that motives have a 6-functor formalism. And this is a theorem which is by Joseph for the algebraic situation, and for this joint work with Joseph and Martin for the rigid analytic counterpart. When I say that they have a 6-functor formalism, in particular, I mean that if something is proper and smooth, then the associated motive is dualizable because of some formal nonsense telling you that F lower star, if F is proper and smooth, will map dualizable objects to dualizable objects. And now, to answer Ofer's question, this also means that in the category of motives, you will also find motives of something which are singular over X, just by taking the appropriate motive constructed using the 6 functors. You may also find motives with compact support and all the variants that. Let's say that here what I'm using is that you need some projection formula. You need that F lower star is F lower shriek if F is proper. And then the usual fact, you have F lower shriek, F upper shriek, left adjoint if F for F upper star if F is smooth.
Okay, so you need those functors without finiteness condition, and you need some projection of finiteness.
Exactly. So I'm regaining some finiteness condition out of the fact that being proper and smooth means that the associated motive is dualizable. Implies that the associated motive is dualizable. Exactly, by some Kunet formula. And dualizable objects here have been proven to be perfect complexes by work of Clausen, Scholzen, and Andreichev. And so we have that. And now how to prove that they are vector bundles and not simply coherent? So in order to prove, use this to say that the motive over S of X is dualizable. So it's sent to a dualizable guy. And now in order to prove that these HIs are even vector bundles, you use the spreading out result. In what? How? You can use spreading out. Why? Because if I have a coherent module, in order to test that it is a vector bundle, I can test it around each classical point, like k rational points. And around any k rational point, my motive is constant. That's because, so I can use by testing around each k rational or c rational, k rational point. Now I'm using the fact that motives over my k rational points are the union of motives over its open neighborhoods. So this means that up to taking a sufficiently small open neighborhood of my point, my motive will actually come from the base. It will be a pullback of something constant. And yes, which it is, because I am dealing with dualizable, coherent modules. Now I know it is coherent, I want to prove that it is a vector bundle. Okay, so this is just a sketch of a proof. Let me be a bit sketchy here. And now I want to move to the other questions that I briefly introduced in my introduction, namely how to go back. So from the generic fiber to the special fiber. So now the question is somehow the following. I have a generically smooth family X over a base S, and I want to define something like, which might be singular at a certain point S in S, and I want to associate to it something like the limit as S, as maybe S bar, as S goes to S bar of XS. And this guy should not just be the singular special fiber I would find over this point. It should be something more refined than that. It should somehow maintain some extra information, namely the fact that it arose as a limit of a generically smooth family. So how to do that? So this was more classically denoted with the letter psi and called the nearby cycle of the family X. Okay, so how to do that? Let's focus on the absolute case. So let's pick K, a perfect field of characteristic P. And as previously done, we found out there is a functor from dAk, and let's fix K to be a non-Archimedean field having K as a residue. Okay? Now, we saw before that we could identify this with motives over OK, and therefore go to rigid motives over big K. And the question is, how big is its image? So by standard nonsense, so the actual theorem definition, let me denote with this decoration, U and I, unipotent motives, to be the category spanned by the image of this functor. And closed under co-limits. So it will be a full subcategory here, the one generated by objects coming from this functor. So as you can see, it is generated by things which have good reduction, because everything that has a smooth model here will be in this image, And I'm exactly taking everything I can construct here as extensions of such motives of good reduction. Now, it turns out that, so who can I find here? Definitely a motive over K of X if X has good reduction. That's by construction. But not just those. I can even find out those that have semi-stable reduction. In the sense that if X has semi-stable reduction, there is a way to construct it as an extension of various motives, each one of which has good reduction. So, OK, great. And then the theorem, which is part of a joint project with Federico, Binda, Martin, and myself, is that it gives you an explicit description of this category in terms of what's happening over there. It is equivalent to the category that I can denote with DAN of little k, which is defined as follows. So this is the category in which I'm taking objects M inside DAK, and I simply take a map, a monodromy map, from these motives to their negative shift twists. So this is just the description of the compact objects, and as usual, this will be a compactly generated category generated by such objects in which M is compact. If you prefer, you can describe it as being the category of those maps, but which are in the nilpotent.
Why do you know that N is nilpotent?
By weight reasons. So there is a drop of weight here. If this guy is compact, it has bounded weight, say AB. This would be either A minus 2 or A minus 2, B minus 2, or A plus 2, or B plus 2. I don't remember. Anyway, you know that after a sufficiently many iteration of this N, you have two motives that have weights concentrated in incompatible intervals. We have a theory of weight for motives, for classical motives, algebraic motives over a base, by Bondarco. This is one way to see it. OK, which implies in particular that we do have a theory of weights even at this level. So this category is automatically endowed as well with the theory of weights, a la Bondarco, by defining a weight of your object as the weight of M, morally. Yes, maybe. I don't know. Probably.
You're going to see the M of X that come from potentially single X?
So yes, there is a way to describe it explicitly. OK, but this is just what this isn't the theorem. So this, again, this is not technically, this is not a definition. These are just the compact objects. But I mean, morally, you can say that. So once again, how to find out a proof of this fact? Well, you can apply the so-called Barbach or Barbach-Lurie theorem to this functor, which is a monoidal functor that sends compact generators to compact objects. So by Barbach-Lurie, we have that this category ReachDA unipotent, K, is indeed the same as a category of modules over the source. And the ring object is obtained by taking the right adjoint to this functor, which is typically denoted by chi, so chi of 1. And now you have to make an explicit computation of this chi of 1. And fortunately, you can do it in the sense that chi of 1 will become the motive of GM. So it's simply a split extension of 1 and 1 minus 1 minus 1.
So chi is an adjoint is
Right adjoint.
right adjoint which exists by this.
No, no, no. The existence of chi was just formal blah, blah. All these maps are in PRL. And Barback tells you that under certain hypotheses on your functors, you always have that the target category can be described as modules over a certain ring object, which is the one arising from this forgetful function. Exactly. Mm-hmm. OK, great. Now that we have such an explicit description, which was even given by, I mean, this theorem, a version of this theorem was already known in equicharacteristic 0 by Ayub, let's say up to now. This is Ayub or AGV for more general statements. And now you can you just study some Koszul duality, some instance of Koszul duality, telling that the structure of a module over this square zero extension of 1 is simply given by one operator, which is this monodromy operator. So the structure of a module over here is the same as this map. And now I'm cheating a little bit, because in this computation, we are actually choosing a pseudo-uniformizer of K. OK, so a priori, this identification depends on a choice of a pseudo-uniformizer, which is not at all absurd if you think about how even the classical monodromy operators are defined. Good. But then, now, I wanted to go back, right? But instead, I've described to you the image of this functor. So why this helps us? Well, there are two remarks. First of all, as this category contains everything that has semi-stable reduction, when you consider it over CP, say, then it fills the whole category because of a well-known fact by using de Jong's alteration that any rigid analytic variety over an algebraically closed field locally admits a semi-stable model. Or maybe there is an alteration, blah, blah, blah. And so now that we have Q coefficients, we have that. And you remember that rigid ACP was even the union of the various motives you get when you take finite extensions of my QP. Meaning that if you have now your favorite motive, say over QP, you know that after a sufficiently large finite extension, it will become unipotent. So for any M in rigid AQP, maybe compact, then there exists a finite extension of QP such that MK is in unipotent over it. Yeah. Yeah, actually, it is true for even polystable reduction. So something which is much more general, and I think would take into account all these potential definitions you have in mind. OK. So corollary, we have a functor from rigid A. So from now on, I will stick to the case of CP, because in order to handle the case of QP, you just have to insert some Galois descent datum in order to reach out and then descend back. So let me stick to the case of CP. So we have this functor which morally is sending an X, say as smooth rigid analytic variety over CP, to a pair, which I can declare to be its nearby cycle functor, together with a certain monodromy operator. OK? So in case my variety had honest, good reduction, this is nothing but its special fiber. But in case it had only semi-stable reduction, say, this motive can again be described out of the geometry of the special fiber in the same way as in the classical work by Steenbrick, Mokran, or Rappaport and Zink, who considered this complex in each individual realization. And as a further corollary, So every time you cook up a cohomology theory for algebraic schemes over FP bar, well, then you have automatically another realization for analytic varieties over CP. So if you take, so I don't know what are your favorite cohomology theories over a field K, but let's think about, I don't know, L-adic. I can take rigid, the rigid cohomology, so say K is in characteristic P. In using the good old method above there, I can actually specify my thing landing in WK 1 over P, right? So this will land in quasi-coherent of WK 1 over P. And yes? Or maybe suppose for a second that K was C, you can even take mixed Hodge structures, like the good old Hodge realization for motives over C. So, I mean, these two arrows are alternative one to each other. So once you have that, you can extend those as realization functors, as cohomology over for region analytic varieties over the generic fiber, and where they would land? Well, to the same category, except that now you have an extra datum, which is this monodromy operator. So you land in here, which are like L-adic phi n modules, also known as Weil-Deligne representation, and this will be the Weil-Deligne representation attached to your unipotent motive over C. In the second case, you would get something like this, but you also have a Frobenius descent datum because we have factor over in characteristic P, and here Frobenius is invertible, so you can always endow this as well with a Frobenius automorphism, and plus you have this monodromy operator, and these are what people call phi n modules. And this realization is the Hyodo Kato realization. So one of the precious ingredients in defining, I don't know, symptomic cohomology or other P-Adic cohomology in characteristic 0 is this Hyodo Kato realization. And finally, I have the so-called limit Hodge realization as defined by Steenbrink or Clemens and Schmid. This was the first one that had been introduced in the literature, once again landing in the same category, now with an extra datum, which is the monodromy. And not only do we have an alternative and streamlined definition of these facts, but we have extra properties that were not known before. For example, a weight filtration and the presence of a so-called Clemens-Schmid chain complex for Hyodo Kato, which among the three is probably the most mysterious one. Okay, now you may wonder, how do I know that this cohomology I constructed formally agrees with, say, the Hyodo Kato cohomology that had been defined by previous people in the past? Well, it turns out that by construction, you see, this category is nothing but DANK. So in order to say that one cohomology theory agrees with any other, you can do it in two steps. You first look at good reduction things, and you say, yes, Hyodo Kato does extend rigid cohomology. And then you wonder whether it is compatible with the monodromy operator. And this compatibility with the monodromy operator can be tested on one specific motive, which is the motive of the Tate curve. Because the Tate curve contains precisely the somehow free monodromy map you can have, and if the two agrees on there, they automatically agrees on a random motive over here. So it's not like an alternative Hyodo-Kato, it must be Hyodo-Kato. So let me end with this geometric picture maybe. So consider for a second the A-inf, the generic fiber of A-inf. So SPF of W of O CP flat, which I like to describe like this. So here we have the characteristic P point, CP flat, and on its opposite we have precisely this WK 1 over P point. This is the one way to think about it. And so this theorem is telling you that once you have X over CP flat, by the spreading out, you can spill it over around this point onto some actual open neighborhood of this point into this curve. So this X will spread out a little bit. And now you use the Frobenius descent, the Frobenius datum you get in here, because it's a characteristic P situation, in order to glue together these extensions along the Frobenius, which is acting on this space. So this Frobenius can be interpreted as a gluing datum on the spread outs. So this allows you to extend your family over covering practically all of this space except the final point, because you cannot reach this final point. So I'm doing something like this. And then I land formally on this y0 infinity. And if you can think of Hyodo-Kato cohomology as being the cohomology theory which is filling the blank at this level. So if I have an X which is now covering this space, I can take the relative de Rham cohomology. This will define a quasi-co, even a vector bundle on this Farfontaine curve. And now the Hyodo-Kato, I don't know, we thought as the limit of this vector bundle onto this missing point, because this also behaves a bit like a puncture disk. And the monodromy operator, you see, makes sense because it's as if we are going around. But this is just a geometric idea. What's more important about this picture is that you can play the same game for an arbitrary perfectoid space. Now, if you start from a perfectoid space over here, you can do the same magic trick. And there is this theorem obtained with Arthur, César Lebras, for which this construction, if you start from a perfectoid space in characteristic P, you can go to motives over the whole space. And then if you restrict them to a certain divisor, which is linked to a certain untilt of your P, then the composite map is an equivalence of categories. So we have a tilting equivalence for motives, but at the level of smooth varieties over the two bases. Okay? I think my time is over, so thank you.